I'm Italian, I like to pace and move and gesticulate, so I'll try to stay close to the mic, but it'll be difficult. My name is Piero Polissone. I spent most of my professional life at GE Global Research, which I joined in 1979 as an individual contributor, and the last 7 years of my tenure was as a chief scientist in analytics. And I enjoyed tremendously. So most of the work that I'm presenting here is a reflection of my career at GE. Okay? And it's all public domain. So first a reflection. We all like acronyms like AI, computational intelligence, machine learning. And there are some taxonomies, and we're all engineers, or tend to be engineers in this audience. And we can look at some of the traditional engineering disciplines, traditional AI, rule-based, case-based, probabilistic reasoning. Computational intelligence is nothing else than nature-inspired AI, if we want to use a label. So, and machine learning, which used to be by itself, has been claimed by both, so that's why I put that dash box. Okay, so we have all these disciplines, but we're in multiple places, and the problems are over there, right? So I'm sort of subscribing the MathWorks approach of toolboxes, right? There's not a single tool that solves all the problems. We need to be able to put all these disciplines and knowledge together to solve real-life problems. And I'll try to illustrate that throughout my presentation. So this was the title, and I tried to parse it a little bit. Industrial Internet was a term coined just before I retired by my boss, who was wanting to contrast it with consumers' internet. And nowadays, I think we refer to it as industrial AI, but it's still the same, because the labels changed based on marketing. We'll talk a little bit about that, then a little bit about PHM. What is PHM? Prognostics and Health Management. And why does it matter? At least for the industry, it matters a lot, right? Is keeping all the equipment alive, borrowing some terminology from medicine. Then we're looking at the evolution of analytics for PHM. And I'll give you a very brief history of my past at GE, as I went through different roles, as I was better understanding how I could survive and provide value added. And then we'll touch upon some research topics and conclusions. Okay, so to be a little bit dramatic, as part of my Italian nature, we can look at 3 ways of revolution. Right. The first one is the industrial revolution. We all know that with the advent of the internal combustion engine, we had an impact on urban centers, the centralization, big hit on the environment, resource intensive. We created a lot of emission, let's put it this way. But that was 150 years ago. Then the other revolution was probably some 50 years ago when we had TCP/IP and packet switching among servers. There were very few big servers in the nation, and we have very few networks for those. And that's the precursor to what we understand now to be the internet. Okay. And the most recent one is internet for the machines, not for the people. Having a large number of smart machines all interconnected, with some people as well involved in the communication, the machine gathering, creating a lot of data, where the term big data comes from, and then trying to make use of this data at various places in distributed fashion. So that is what industrial internet is about, and it has sort of 4 pillars in my view. One is the IoT, which is also well known, and I'm trying to say there are many societies that have their sweet spot in each of these columns, right? So in here, sensors are becoming very, very cheap and ubiquitous. We do signal processing sometimes at the edge. Communication is what you need. Cybersecurity is perhaps the most important of all, because without that, you cannot have critical or mission critical applications. And you have to display that information on mobile platforms like this one, and be able to be digested by people. So there is a lot of UX as well involved in that. The second one is big data, right? Oh, I'm sorry, the smart machines. And so you need resilient machines, and Again, there is a control system society that has a lot of resilient control conference devoted to that. I participated in some of that. So there are different disciplines, all of which combine into the big picture. The third one is big data, right? And big data basically requires a technology stack that so you can absorb or ingest the big data, manipulate it. It typically lives in the cloud. Didn't used to. It used to be on local cluster. I'm a Berkeley fan. Well, I mean, Berkeley is my alma mater. And some 6 years ago or so, there was a lab called AMP, which stands for Algorithm, Machines, and People. Algorithm was machine learning. Machine was basically the operating system toolbox, and people was crowdsourcing. Okay, so the idea was how can we end up looking at the intersection of all three. Now there is a new lab that is taking over that. I should say it's a continuation, and this is what I'm trying to focus. Right, machine learning. There is also more traditional analytics coming from OR. Again, there's lots of analytics traditional engineering, but I'm looking at data-driven analytics, and that is sort of the sweet spot for the computational intelligence society within this IEEE Federation of Societies. Okay, so that's the menu of what we're trying to do. Now that we have all this technology, we need a focus, an application focus on using PHA. The question is why? Well, I used to work for a very large industrial company, and I needed a business model to get funding for my research, applied research, or contract. And the business model is simply here. You have a large fleet of equipment. Each piece of equipment is worth $4 or $5 million each. You have MRIs or CTs. You have aircraft engines. You used to have locomotives, not anymore. Turbines for generating power and so on. And they're sold to the utilities or the railroads or the airlines that have a warranty period, after which they still want to use it, right? So you have to provide maintenance. And the old model was, well, we wait until something breaks and then we'll call them, right? And it was a lose-lose because, building parts and labor was not a business growth model, and the customer had a lot of downtime with very expensive equipment. So the idea was to switch the responsibility to the OEM before something happens and change from unplanned to planned maintenance events. And that's what PHM enables. So now we're going to go through PHM and try to understand how that happens, and then try to understand how machine learning helps that process. Okay. So typical cascade, engineers like cascade. Well, sort of obsolete for software development, it's still good to understand the processes. So initially you acquire the data, and remember you don't have 2 or 3 units, you have tens of thousands of aircraft engines flying right now, right? And you want to collect data on the wing of the flying. So telemetry used to be a problem, not anymore, but the same is true with turbines generating electricity. So you acquire the data, and you try to see any unit in this fleet. I'm using fleet, doesn't matter if it moves or not, right? As a collection of units that is deviating from some baseline of normality that you have established earlier on. If so, and I don't want false alarms there, I should be able to figure out why, and that's diagnostics, which is root cause analysis. Once I know that, the next question, which is the most difficult of all, is how much life do I have left? When am I going to die as a machine, right? Prognostic is basically estimating remaining useful life within safety margins. It's difficult to predict the future, as Yogi Berra used to say. It's difficult to do it with a small variance, such that the prediction is actionable. What do I mean by that? If I'm trying to say this engine will have to be overhauled in 20 cycles, which is 20 flights. plus or minus 15 is not useful. If 20 cycle plus or minus 2, it is very useful. So the second one, the second prediction is actionable, the first one is not. So prognostic is all about reducing the variance of the prediction to make it useful. Once you have that, you have a horizon over which you're optimizing your intervention, which is repair, supply chain management, level loading your repair shops, and so on. Sorry. And so up until prognostic, you have invested, and after prognostics, you are making money. So how are you making money, by the way? Because with the contractual service agreement, it's like paying an insurance premium from the customer point of view, right? It's a fixed premium, and the OEM sees this revenue flow over time. And then the cost of executing the contract is on the OEM. So if I can prevent large damages because I can identify it early enough and I can schedule it, remember, it's on their nickel to fix it, right? Then they reduce their cost, they increase the profit. And so this technology has an impact on the bottom line rather than the top revenue, top line. And that's much more impactful, which is why we invest so much in machine learning and similar techniques. The reason for these stars is because out of this, the two most difficult aspects is anomaly detection and prognostics. Anomaly detection is because it's very easy to cry wolf. Right? I said, oh, there's a problem. If there is a problem, then you're cascading all that series of events for nothing. You're losing credibility, it costs you money, the manager is not going to be happy, and so on. Right? So you want to stem or reduce the number of false positives, especially because you tend not to have too many false negatives. But it was very interesting when they asked engineers, I'm guilty of that, right? What is the value of this, that these variables can take under normal operations, and when does it become excessive? And so if the value was 10, the engineer will cover his or her base and say 8, right? Because it's definitely safe at 8. Well, between 8 and 10, you're causing a lot of false alarms. Number one. Number two, you're looking at one variable at a time, which is like if you have a covariance matrix, you're only looking at the main diagonal, at the sigmas, right? Instead of looking at the entire covariance matrix and see when the relationship among the cells are disrupted. So those are reasons why you have false alarms. I'm going to skip that. Now it's clear that anomaly detection is unsupervised learning, diagnostic is supervised classification, prognostic is supervised regression, and optimization is in the actions, right? So let me quickly explore the waterfall. I want to be aware of the time because I tend to talk too much, so I'm going to manage my time and skip to some critical places where we need it. But data collection is very simple now, basically. Sensors are ubiquitous, they're becoming reliable, they're cheap, storage is coming down in cost. We still have some quality, in particular with data cleanup. Any of you who have done data-driven models knows that the problem is not in the model, the problem is getting the data right before you even touch a model. And going from data to features takes a lot of time because so much data is spurious or has wrong labels, or the labels are inconsistent over time, or we decide to switch units midstream without telling you, right? And or they just not used and so on. So at Berkeley they had something called, I forgot the name, and I removed the slide, but it was a way of sort of sampling some data set, subset of data set, to do the cleanup automatically and then see if it would work for the rest of the data set. Basically trying to automate that process that used to be a manual process. Okay, that's, there it is. It's sample clean. But this is what I meant by technology stack, right? And this is what you expect from either providers or from, you know, Apache project have, I think they maintain Mesos and Spark and a few more, but all this came from Berkeley AMP Lab. And anomaly detection, I'm going to switch a few, skip a few slides, but the whole point is to remove false positives. Everything else is about right. Some of the best way to do it is not by tweaking the model and refining it best as you can, but using multiple models that have somewhat uncorrelated information, and therefore would be diverse enough to make somewhat uncorrelated errors. And by taking the fusion, you can reduce the false positives. This is an example of something called the Hopland T-square back to 1935. Okay, statisticians already had a good idea of, let's look at the whole covariance matrix instead of just a mid-diagonal, and come up with the score that will say when something looks like an anomaly. You can barely see this, but you can see that the score goes high up, and then you can call an anomaly when you reach a certain threshold. I mean, this is to say it goes back to the mid-30s. We can make it a little bit better with a collection of techniques. All these are from computational intelligence domain. We have over here, these are the mouse on the screen. These are called all-associative neural networks. Okay, and basically the frame to claim is that the output is going to be identical to the input, right? Which you can, of course, obtain by putting a wire between input and output, but you're not learning anything. So the idea is to train them enough to learn the covariance matrix information. If you can, I'm going to go away from the mic, drives me nuts. If you can see, you have several inputs, and then there's a choke point. So think of these as the largest eigenvectors of the covariance matrix. And out of this, you should be able to replicate, with a good approximation, the outputs. So by doing so, you are creating the equivalent of a virtual sensor. Because with the correlation that the inputs will have, right, that information with the covariance matrix, even if this sensor is out, you should be able to predict the output of that sensor based on the other one. So that's good, but like most global models, if you only use one network for the entire feature space, it has to do too many trade-offs. So you want to use local models in different regions, and then have a supervisory that switches from one model to another one. Or better yet, it's not blending two models, it's fading one out and fading the other in, which is an interpolation of models instead of a model selection. That's how fuzzy supervisory work in control. And then, because we didn't know exactly what, so we had three rules, and these were the membership function of the rules corresponding. I have to go here to be able to read because I can't read on the screen. But so this was map number, which is the speed because of the map, and the temperature and altitude, right? And those functions were my initial assessment of what was a low altitude or a high altitude. And then I said, let's use an evolutionary algorithm to fine-tune those terms so it will optimize some figure of terms. So I'm skipping the process because it just takes too long to do that. Of course, we used a thermodynamic simulator that was built at GE for a decade of engineering year. Actually, it's engineer decades, not engineer years, right? And that was the evaluator of all that. And having done that, we were able to pretty much tell if something was an anomaly due to a system deterioration, which is as a very, what you're looking at residuals of between what the physics-based determines the output of the sensor to be and the actual output of the sensor. And you can see that you have very smooth degradation when it's a fault of the system, versus here we put a step function in one of the sensors, and you don't have to do pattern recognition to recognize a different signature. So that was very important to eliminate false positives in anomaly detection. Again, there's much more to be said, but I want to leave it this way for the sake of time. Diagnostics is also important, but diagnostics has been studied for much longer. And we pretty much understand what classifications are. And again, the best way of doing it is, in my view, is with an ensemble of diagnostic models. And this is an example of a CFM56, which is sort of a workhorse aircraft engine. And it had multiple gas path faults. And without going into the details, we used 3 classifiers: a neural network, an SVM, and a CART, classification analysis regression tree classifier. And then we said, okay, these are the overall accuracy, but if I take a fusion of the 3 and I do the average, I get 85. But if I know that one of these models is better in this region of the state space and another model is better over here, I want to leverage that knowledge. So I compile it before I start using it. Once I have the model and I have the performance, I compile that using CART trees, right, with the error as my signal. And when I have an input, I just drop it into that tree and figure out the expected error that the model is going to make. Okay? Then the weight is the inverse of the error. Very simple. Dynamic fusion is like, I used to call it meta-lazy learning. Lazy learning is something that came out in machine learning, saying you don't need a model, the model is the data. Right? Find the neighbors around the query points within the data. Here I'm saying do that at the meta level by determining the weights of the models. Okay? So prognostics is, like I said, the most difficult part is there are many issues. Best way to show you, how many of you are familiar with random forest? Those of you who did not raise your hand, go Google it. I'm serious. It's the best thing you can get out of my presentation. Become aware of random forest. It's very simple to use, it's very intuitive, and it's very powerful. It's embarrassingly simple. You have to make it a little more confusing when you're presenting it, so it looks difficult, but it's not. And it was Brayman, a statistician from UC Berkeley, who developed it in '99 and then published in 2000. And basically says, okay, if CART trees are good, it's one tree, decision tree, a forest will be better, right? Which is a collection of trees. And he used 2 concepts to inject diversity, that is low correlation, in the forest. One was bootstrapping, which is I'm going to sample with replacement my records. And in so doing, I only have like 67% of unique records. Right? So some of them will be repeated, and I'm just not going to store them repeated time, just put a counter at that record. So whenever I do that, it will count that many times. So think of your data matrix as rows and columns. The rows are your records. You only have 67% for each model, unique model, very unique records. And the columns are your features. Well, guess what? When I'm going to use, when I add a node and I want to expand the node into a subtree, I'm only going to use a random subset of the features, not all of them. If I have 100 features, I'm only going to use 10 features. So 100 chose 10. Pick a point. That 10 tuple will be used here locally. A different 10 tuple will be used here locally. I'm injecting diversity because I'm depriving the model as I'm creating it systematically with some of information. So it's going to make different errors. And by making different errors in the forest, that's going to decrease the variance of the fusion. And you can do the math, it's very simple. Okay? So this we did for some airlines. They promised to keep them unnamed, so I did. This is airline A. And it's real data. We had parametric data, then sensor data, and then there were non-parametric data from the FADOC and the CMC, which is what Boeing uses, the Computerized Maintenance Center, something like that. I don't know. I can't remember anymore what it stands for. And we were asked to say, well, can you detect if you can find any flight deck effect? flight deck effect is something that has to be reported to the FAA, causes delay or cancellation. That is, it costs money, right? Over the next 5 times without any false alarm. That was, and so we did, and with I think I forgot to put the output there, but it was like 80 or 81% of previous undetected flight deck effects, which we could anticipate. So then they say, well, what happens is, you know, first they give you a problem, and then when you solve it, say, well, it's too easy. Too easy because 5 flights away from the failure is, you have a lot of information and visibility into what is going to cause the failure. So we said, what about 100 flights away? So the window now was, the horizon was 100, and using the same concept, we were able to get 41%, which was remarkable. And this is the horizon that I mentioned earlier on for prognostics, right? You want to be able to say, how much longer do I have so I can plan something in between, and instead of being surprised, broadsided, and it cost me a lot of money, by planning it cost me much less. That was a business model. It's time to switch. So evolution of analytics, I decided to be very self-centered. That's me. A few years ago, when I did the first expert system for GE for locomotive troubleshooting, and I was this guy, right? Pulling a rabbit out of a hat, speaking some fancy words about AI, and being the high priest, that is a knowledge engineer, who was talking to a subject matter expert, who was Dave Smith over there, and then encoding his knowledge into rules. It was a rule-based system. It quickly dawned on me that it was a terrible way of maintaining job security, because I was young enough who could touch the system and make changes and keeping up to date, and I wanted to do something else as a scientist, right? So that motivated me tremendously to say, hey, that job is sort of a, this cartoon is to sort of show the scientific methodology where you have some theory, right? And you run some experiments to validate the theory, or at least try not, you want to see if you find a counter-example to the theory. And then eventually, so think of this as being back propagation. And now you have, with a few actions, you have some software that works, and this is your neural network in MATLAB, the toolbox, right? That doesn't make you an expert in neural network just because you have a license. So you have to figure out how to do all this problem formulation, specs, design, functional validation, compilation, performance, and so on. And if you don't like it, right, you don't like it to run the experiment, you start tweaking it. Well, it's, like I said, it's a great job security, but you're the slowpoke in that, right? You don't want to be in that loop. You want something faster than you to be in that loop, trying out different things. That's what computers are for. So what you want to do is extricate yourself from the loop and go upgrade your role, right? Go one level up. And that's what I did in the 2000s. Still employed, that's good. So we started using evolutionary algorithm to grow population of models, right? And then perhaps take the top few to create a new sample. And the fusion was still static, but I was learning on the fly, and that was already an improvement. And I love the type of job. The last few years at GE, I used to give talks around saying how to destroy my job. And that was because with the cloud, you shouldn't be able to do this at all by hand, right? There should be a lot of mini-me's in the cloud trying to do that, and I should do them at a scale. I may decide to do it in complementary or competitive fashion. That is, I could divide a large state space into both different disjoint subspaces and do fine-grained simulation in different subspaces and then put it all together, or have competition to find the best model. And speaking of competitions, 5 more minutes, and then I'm trying to finish on time, but I may ask for a few extra minutes. I start looking at what are the research topics that one ought to look at. And let me see if I can the next clip. So the first one is the 3 V's. Velocity, volume, variability. One could add veracity and value, but those are just buzzwords. Basically, you need to be able to handle this at large scale and at large speed, right? And the variables are very heterogeneous. There is variability. And usually that's what software vendors and organizations devoted to building technology stack will address. Okay. There are so many things that you have to understand. What is it you're going to outsource, and what is it you're going to focus on? If your research is on big data, software, operational systems, software tools, that's your field. It wasn't mine. This is the Achilles tendon. There is a Moore's law for computers. There is no Moore's law for humans. 5 years from now, computers will be so much faster, much more storage will be larger, memory, bandwidth. Our brain will still be the same, right? It's a little bit somber to think about it. So we need help, especially to visualize performance in high-dimensional spaces. And so there is a whole, this is extreme scale visual analytics. Many, many issues that touch this interface between people and computers. And when you have big data, we also have a large number of models that go with it. It's not just the data, it's the models that go with the data. And who's going to maintain those models? Not you. I had problem maintaining one model. So you have to think about model maintenance. How do you keep the models alive, vital? Streaming versus batch data analysis is a big dichotomy because very different things you can do. But let me focus on one thing out of this, which is the one with the fusion. Another talk will be talking about some of the other sections. So in this one, I want to say there is perhaps let me touch upon these two. Physics and data-driven models. Physics is not something to toss away. I mean, if you want to have credibility in the industry, you must respect all the talent that went into the physics-based model that industry created over time, which are difficult to maintain and upgrade, but are still there. And so instead of saying, oh, I can do better because I just got my master in data science or machine learning. No. What you do is a model is a mapping from X to Y, correct? So you use a physics-based model to go from X to Y hat, which is the ideal output if all the conditions, all the assumptions with which a model was built were true. And then you go from Y hat to Y, which is the actual. You take the residuals, the difference between the two, and you apply machine learning to the residuals. It's much better than trying to go from X to Y with machine learning. And that's how you're leveraging the knowledge that the engineering group in that industry had, not to mention the fact that you're making some friends instead of some enemies. Right? And it's a matter of credibility. The other that I want to mention is just the model agnostics. This one, and then I'll jump to the conclusions. So the idea was, I mentioned CART before, C-A-R-T. Right? What CART does is says, if this is your feature space, it creates some hyperplanes. So this tree with 4 nodes has created hyperplane that says if this variable is less than that, then this. Else, if it's greater than that, and it will do that, right? So the idea in CART is a minimization of entropy or G index, so it doesn't matter what it is. if it's a classification, if it's a regression, it's variance across all the nodes in the tree. And then you say, well, I'm using that as my index in a database. So I'm going to have a database of models, and each model will have a cut tree that represents its performance on the test data. When you give me an input, I'll just put it in the tree, and it will fall into one of those nodes or regions, right? And that will tell me the local statistics, what is the expected error and the variance of the error. With that, I should know, well, this is a good model or a lousy model. And if it's really lousy, I may not want to use it, or I'll simply take something because I don't want to be part of the decision maker. So just say the weight of this with which this model contributes is inverse proportional to the error, right? And then I normalize the weights, and I'm in business. So we did that for this particular program. How many of you are familiar with Kaggle? Okay. So Kaggle used to be called the Fight Club for nerds or something like that. And basically, it's a competition where people compete for a variety of prizes, from money to kudos and credits, right, in the community, to solve a problem, which is a challenge. And so our challenge that we sponsored, I think it was 2013, was 28,000 flights in the United States every day. We want to know the expected runway arrival, ERA, and then the expected gate arrival, EGA. So clearly, the first one depends on the weather and the flight condition or not. The second depends mostly on the ground situation in that particular airport. Right? And I think it was a group from Singapore that won. I mean, from all over the world, we had competitions. And we gave 5 prizes, so we got 5 models. Unfortunately, marketing set up the terms of the competition. We only had 2 weeks worth of test data. I would have liked a much longer one. So I used the first week to learn about the model performance and to do this fusion agnostic. And the second week to say, let me use a fusion. Well, it turns out that the fusion did better than the best model at any day in time. Except you don't know which is the best model until the day is over, right? But the fusion did better in 5 or 7 days, and was second best in the other 2. So again, the idea was let someone else build the models. I'll just build some wrapper on top that leverages. And in this case, by having different groups working with, there's a lot of available inputs, but not everybody uses all the inputs. So again, you want this low correlation of the errors among the models. And keeping my promise to stay roughly in time. Conclusions now. So in my distant past, models were handcrafted, and we had job security. It was a bad job security, but we had it. It was a pain, almost impossible to keep it up to date without, and try to do something else. Then we start using meta-heuristics. Evolutionary algorithms is one of them. To derive, basically to search into model space, both structures and parameters, and create the models. And the point was that if you can create the model from scratch, you can also update it with the same process, which is critical, okay? And then start using some ensemble with static fusion. Then we now have the agony of choice, right? We have so many tools that are already available on the technology stack, and you have to figure out what is the best value added that I can have as my machine learning, as a machine learning expert / data scientist. There is a mixture of those two concepts. A data scientist, the joke was data scientists and statisticians who live in San Francisco. But beside that, a data scientist is much more devoted to the curation of the data and access of the data, distribution, and then some analysis. Well, the machine learning guy tends to just assume that the data scientist has done his job and devote himself or herself to the building of the machine. Right? But there is a commoditization, without any doubt, about if you have seen H2O, it's a tool. I don't know how many of you are familiar with that. It basically does everything for you. You have a dial of legibility versus accuracy, right? If you want something explainable or not, and it'll just start creating models after models for you. Incredible. So I think that this is where we are, but there is no way you can deploy any model unless you have secured a path for its maintenance. And by maintenance, I'm not saying, I have a different version of the operating system, I have to update the model. No, no, no. The maintenance means I have new data. Is the performance of the model still accurate? Are we operating away from the training set for which the model was created? Is the model becoming obsolete? And it's very easy for these models to become obsolete. I ran some experiments in my past, and I realized for some specific models, after 1 year, they were just like random selection, completely useless. Anyhow, I tried to portray also a few research themes in analytics, and I have one commercial before I close. That is in May 2021. I'm projecting ahead of time. In Santa Clara, we're probably going to be in the convention center in Santa Clara. We're going to organize the first Computational Intelligence Expo, which will be just invited speakers. We're going to have students with poster sessions because we're aiming for the industry. And our currency as a society of our grad students who have a know-how, and probably the industry would like to hire them. So we want to give an excuse for the students to come, but we're basically aiming at the industry to support this, and it will be on 6 different verticals. But it's something that I'll be announcing as soon as I get the formal okay. So thank you very much. Sorry for taking a little longer, and I really appreciate your patience and your attention.
Any questions?
Yes, please.
First of all, very interesting talk. I have two questions. First of all, you said that we like to use different models for example, to increase the accuracy of detections and so on. My question is that how do you basically switch between the models, or how do you pipeline the models to make sure that you are getting the maximum accuracy? Secondly, the second question is, as you have explained at the later part of your talk, that the training model that has been used for, last year, over time, it's shooting random results. So meaning is that we need to basically have a kind of framework where we can learn continuously from the data. So continuous learning.
Yeah.
Have you heard something or did you?
Oh yes, it's a part of a picture that I skipped because of time. There were A and B section, that was the B section. But back to your first very quick answer. They're not pipelined, they're in parallel.
Mm-hmm.
Okay? So when I say ensemble modeling, they all get the same input in parallel. They all come up with an answer on the same scale, otherwise I cannot fuse it, maybe a PDF, and then I do the fusion. And the fusion could be as simple as an arithmetic average, or as complex as a model that tries to figure out what is the best way of fusing it. So for the second one, yes, there are many things that can be done about model maintenance, and the best way would be to create some features for maintenance, not just features for modeling, that tell you when this model is getting out of specs. And when you're deploying the model, you want to collect the data that the model generated and then the actual, so you know the error. And that will tell you if it's time to revisit the training of that model. And if the development platform was the same or associated with the deployment platform, you can do all that in the same environment.
Thank you. So it sounds like you talk about something like adaptive process in the loop.
Yeah, the most important aspect of that cascade was what I skipped for lack of time. At the end is feedback. That is, I did all this. How was I? Did I do it right? Like, what did I miss? And that feedback is a sort of long-term adaptive process because then that input can be used to retrain the model and fix that problem.
Okay, any more questions? Okay, let's give a big round.